Do you have videos?
Yes, I have videos. I have tested them, so they are working properly. Again, your voice is again breaking.
Good afternoon, sir.
Good afternoon.
Good afternoon, sir.
Ratna madam.
Yes, sir.
मॅडम उषा मॅडम येतात की चालू करायचं आपण काय?
मॅडम म्हणालेत सर पण म्हणालेत येतोय म्हणून.
ओके.
Maybe we'll wait for you.
Yeah.
4 minutes.
Yes.
I'm just seeing that list only.
DP, you are in the college. Is madam joining?
DP is there. Okay.
He's logged in, but Paras is not there in his place.
Check if madam has joined. No. she joined? No, no.
I've written her message.
Okay, okay. I'm just checking the link.
Yeah, you can make a call.
Hello? Maybe you can call.
Yes, madam is joining.
Yes, okay. She's joined?
Sir, Himanshu sir has joined.
Yes, madam.
Good afternoon, sir.
Good afternoon, Amar sir.
Good afternoon.
Hello, good afternoon.
Good afternoon.
Good afternoon.
Yeah.
Good afternoon, ma'am.
Ratna madam?
Yeah, shall we start, madam?
Yes, please.
Okay. Good afternoon, everyone, and a very happy new year to you all. On behalf of Hindi Vidya Prachar Samiti, RJ College, Department of Physics, I, Ratna Jadhav, Head of the Department, welcome you all to this seminar in our RJC Popular Lecture Series under DBT STAR activity. It is our pleasure to have with us our guiding force, Dr. Usha Mukundan, Director, and Dr. Himanshu Dauda, Principal. I welcome our today's distinguished speaker, Dr. Amar Kakad from Indian Institute of Geomagnetism. To start the session, may I request our director, Dr. Usha Mukundan, to say a few words? Madam.
Yeah. Thank you very much, Ratna Jadhav madam. Wishing you all a very, very happy new year. Respected Dr. Amar Kakad, Indian Institute of Geomagnetism, Navi, Mumbai. Principal Dr. Himanshu Davda, colleagues from Department of Physics, and all student friends. On behalf of Hindi Vidya Prachar Samiti, Ram Niranjan Jhunjhunwala College, I extend a very, very warm welcome to each one of you. And I think that this is the best way of starting the new year. Dr. Kakad, I also take this opportunity to thank you and the director of the institute for allowing our students to come and visit the institute. And I think they gained a lot of knowledge because of these interactions. Maybe after Corona, our students will once again have an opportunity to come and visit your institute and interact with you personally. Having said that, I thank you for accepting our invitation and look forward to your talk. Thank you very much, Dr. Kiran Kolwankar, Ratna Jadhav Madam, Head Department of Physics, for this great initiative. And students, enjoy. And I'm very sure learning is a lifelong process and you will take some new message from here today evening. So thank you very much. Ratna madam?
Yeah. Oh, sorry, I was somehow mute on. Sorry, madam. Thank you, madam, for your encouraging words. May I now introduce Dr. Himanshu, our principal, a few words.
Yeah, thank you, Ratna madam, and very good afternoon to everyone. Our respected guest speaker today, my all colleagues from physics department, teachers from the other department, and dear students. As I have the institution, I extend a very warm welcome to all of you for this lecture series. Academic engagement during the lockdown period has been possible due to proactiveness of Director Madam, wherein this is the third popular lecture series we are organizing. And our guest speaker is going to talk on plasma wave processes in Earth's magnetosphere. For me, as a non-physics student, it's more of a curiosity than the subject learning. But I love this curiosity because I think curiosity is something which puts you on the path of learning. So thank you, sir, for accepting our invitation and being with us. Our students are going to interact with you as well at the end of the lecture. So students, please play your role. And I thank Ratna Madam and her team for organizing this lecture and inviting me today. Thank you, everybody.
Thank you, sir. May I now request my colleague, Dr. Kiran Kolwankar, to introduce Amar Kakad. Over to you, Kiran, sir.
Yeah, thank you, madam. It is my pleasure to introduce Professor Dr. Amar Kakad. He did his MSc in 1998 from Amravati University. Then he joined Indian Institute of Geomagnetism in Panvel 2005, where he finished in 1999, and then he finished his PhD in 2005. And then he continued there as a fellow, as a reader, then associate professor, and present he is a Professor E. He has received several distinguished awards. He has received URSI Young Scientist Award in 2008. Then he has received APRAC Young Scientist Award in 2010. He received JSPS Fellowship, which is a prestigious fellowship for postdoctoral fellowship in Japan. And he has also received Boycast, which is also prestigious fellowship given by Ministry of Science and Technology. He has 45 research papers in international journals. He has guided 2 PhD students and 12 MSc dissertations. I request Dr. Kakad to start his presentation. There is an announcement for the students and participants that they should ask. The questions will be taken up at the end of the session. They should type their question in the chat box. We will read them out, and then we will have discussion at the end. Thank you. Dr. Amar Kakad, please start your presentation.
Yeah. Hi, everyone. Happy New Year to all of you. So first, let me thank the RJ College for inviting me to give this online seminar. Basically, in this talk, I will be presenting some of the plasma wave processes in the Earth's magnetosphere. In addition to this, like how computer simulations or computational techniques one can use to model these plasma wave processes will also be presented. So let us start with this title contain like few words which may be unknown to the non-physicist. So one is like plasma. Anyway, waves are everywhere. Everybody knows about waves. And then there is a term Earth's magnetosphere. Okay. So in between talk, I will highlight these terms on few slides. So let us start with the Earth's magnetic field actually. This Earth's magnetic field, we call it geomagnetic field as well. So this is a magnetic field associated with our planet Earth. It is primarily dipolar. So we can see the magnetic field lines, basically, they are dipolar in nature. Okay, and it has two poles, North Pole and South Pole on the Earth's surface. So away from the surface, if you go into the space, this dipole becomes distorted. Okay, and you will see some different picture. So this magnetic field intensity on the surface basically varies between 25,000 to 65,000 nanotesla. And if you see the geomagnetic field intensity, it is stronger at the poles, okay, north and south pole, and weaker at this equatorial region, okay, near equatorial region. So this was about the dipolar configuration. As I said, if you go to the space, then you will see this kind of scenario, okay, the configuration of Earth's magnetic field in space. So the field lines basically in this picture, you can see on this side, the field lines are compressed, and other side, they are basically stretched, or you can say elongated at the other side. So what's responsible for making this kind of configuration in space? I mean, magnetic field configuration of the Earth in space. So that's the question. So it's basically, it's our nearest star sun, which compresses the day side geomagnetic field, and it swaps away the night side magnetic field. As one can see, this is a day side, okay, means sun is on this side, and this is night side, okay. And the sun, basically, sun blows out the charged particles, that is ions and electrons, which are energetic, okay. So the flow of charged particles come from the sun and hits on the day side, that compress the day side magnetic field lines, and you will see night side this kind of magnetic field configuration. So ultimately, this flow from the charge particle flow from sun basically disturb the Earth's magnetic field configuration. This is exactly shown by this cartoon, where Earth is saying, sometime the sun just gets me so disturbed. Okay, so what are all those disturbances? We will see that in next slides. So as I said, sun is responsible. Okay, so how sun is responsible, we will see from this slide. So when we talk about the sun, we have always two states. One is like sun, sometimes it's white. So if you see the sun with some sort of telescope, then you will see this kind of very clear, neat feature, okay, on sun's surface. So this we call actually the white sun state. Whereas sometime, if you see on sun surface, you will see some sort of dark spots, okay, this kind of dark spot here, here, here. So these dark spots are called sunspot basically. So if you compare the temperature inside this sunspot with the surrounding area, then the temperature here will be lesser than the surrounding area, okay. But that means they are cooler basically compared to this surrounding, okay. But they are very active in terms of a magnetic field. So if you talk about the size of this sunspot, sometimes you can see here the scale, Jupiter, these are like scaled down. So you can see they are nearly equivalent to sometime, a Jupiter or sometime even Earth. Okay, that much sizes. Okay. So this is one feature where the sun, we say it is in a disturbed state. Another features I would like to introduce here, that is called CME, that is coronal mass ejection. Sometimes what happens due to some activity on the sun, huge mass, okay, huge mass gets erupted from the sun. When it comes towards the earth, okay, then the solar wind, that is charged particle flow, gets intense. The CME can be several times larger than the earth. You can see here, this is earth, and you see how much size this CME has. Okay. So one can imagine how much effects it will have on our near Earth's plasma environment when it comes towards the Earth. Okay, and this is another feature where we say sun is very much active or disturbed. So this panel shows a, a variation of a number of sunspot. This data is available from from the year 1820 to till date. Okay, so we can see this number of sunspot appearing on the sun, okay, towards the earth basically, is showing some sort of periodicity, okay, periodicity of 11.5 year. So we can say that the sun's activity, okay, basically, though we can see this kind of some sort of features, but especially talking about the appearance of sunspot on the sun has a periodicity of 11.5 years. So we can see here, okay, this particular wave cycle, solar cycle. Here it is a maxima and here it is a minima. So we say sun is in active phase when at this peak, okay, whereas it is quite state where this kind of minima occur. Okay, so this is called a solar cycle. So we know now the Earth's magnetic field, that is geomagnetic field, and sun. Now let us see how the solar wind flow interact with the geomagnetic field. Okay, this particular slide shows the animation of coronal mass ejection traveling through space towards Earth. The intense solar wind flow interact with the geomagnetic field, and then it creates basically a magnetic cavity in space, okay, which prevents a direct entry of these particles to our Earth's space environment. Okay, so let me run this. Okay, I have to point option. Okay. Yeah, so one can see this is sun. Okay, and as I said, the mass, okay, coronal mass ejection, a huge mass is coming out of sun and traveling through space, coming towards Earth. Okay, as I said, this is a day side and this is night side. Okay, and once this flow of charged particles, intense flow of charged particles, hit at the day side Earth's magnetic field environment, okay, then one can see the topology of Earth's magnetic field lines basically gets altered or changed. Okay, and rather than entering this particle directly, okay, they follow different path to enter the Earth's space environment. So we will see that one, how they will enter. So this particular process, actually, this change in topology of these magnetic field lines, we call magnetic reconnections. Okay, and through this magnetic reconnection, basically the magnetic energy change. Okay, magnetic basically these particles get extra energy, and then they get accelerated, and then they enter to Earth's magnetosphere. So let me run this complete animation. We can see the particles went night side, okay, and then again the night side, this reconnection is occurred here, and the flow of charged particles come to this night side area, okay, and then these particles basically due to some processes get scattered from Earth's inner magnetosphere, and sometimes they get precipitated in the Earth's atmosphere, where they interact with the gas molecules, excite them, and then emit some sort of colors, okay, in the form of aurora. That's we call aurora borealis or northern lights. Okay, so this color basically around this polar region is nothing but aurora at both the around both poles. Okay, so this is the sun earth plasma system, how it gets uh, it's evolving. Okay, so this is aurora. So yeah, so this is a beautiful picture of aurora taken from our Indian Antarctic station, Bharati. Okay, so you can see sometime, okay, green, then red, sometime blue type of colors, very complex colors, okay, all over, in the sky. So this is really a great phenomena, and how this happened, what's the physics behind this, basically we will I will highlight that particular aspect in my some of these slides. Okay, so basically, as we say now, okay, the Earth's magnetic field basically means the flow of charged particles coming from sun is interacting with the Earth's magnetic field, forming a magnetic field cavity, that is shield which is protecting a life on Earth basically. So we term that cavity as Earth's magnetosphere. Okay, so depends on the plasma characteristics, this magnetosphere divided into different regions. So it's nothing, it's not like, the flow of charged particles come from the sun and enter into the Earth's magnetosphere, and we have, very uniform characteristics, plasma characteristics. No, so different regions will have different characteristics. Okay, so we can see that here that, like, I have noted some of the important region where this flow of charged particles interacting directly to the Earth's magnetic field environment. We call it like the shock gets created. Okay, where we have plasma density 0.6 per cube, then electron temperature is ion temperature, and this is magnetic field. Okay, then we have plasma sphere with this characteristics, then plasma sheet region, this characteristic, and plasma sphere, okay, with this characteristics, and this is radiation belt shown by the pink color, very dynamically active region. Okay, and which is very important for, our satellite communication. Okay, so if you see these numbers basically, okay, so here the temperatures are around 10 eV, 15 eV, here 150 eV and 25 eV. So electrons and ions have, different temperatures, but if you compare them with, when you compare them with the temperatures in radiation belt, then you can say basically their temperature means I'm talking in terms of basically energy, that is kT. Okay, K is Boltzmann constant. So in this area, electrons basically will have energies from up to 200 MeV. Okay, in outer belt, this is outer radiation belt, and the inner belt will have energies of ions like around 400 MeV. Very huge energies they have. Okay, but if you compare other regions, they don't have. So when these particles are flowing, basically their energies in eV, but when they enter into this radiation belt, they have energies in MeV. So if you see, okay, I can say that Earth's magnetosphere, okay, this dynamical magnetic field configuration of Earth acts like a particle accelerator, okay. So EV particles are incoming, okay, entering, and when they reach to radiation belt, they are getting higher energies, okay. So what makes them, this much energized, that we will see in next slides, okay. So when I was talking about this particular radiation belt, okay, now you can see, though outer magnetic field lines are not in a dipolar form, but if you see this inner portion, that's like radiation belt, they have dipolar magnetic field, okay. So these particles basically, when they are entering to night side, they reach this region and they perform a motions, okay. So one can visualize this motion, okay, through a computer simulation technique, okay. So in next slide I will show you that. So this magnetic field lines of the earth basically can be represented by this equation, okay, this equation B equal to this, and the charge particles, okay, their motion of the charged particles can be represented with this equation, okay. Now just imagine if you have just a uniform magnetic field line, okay, uniform magnetic field line, and if I put one electron or ion, so what it will do, it will just rotate like shown in this one, okay. So it will rotate around this magnetic field line, okay. But this is not the picture when you talk about the Earth's magnetic field configuration inside the inner magnetosphere. We have dipolar magnetic field, and as I said, the field is higher at pole and lesser in the equatorial region. So we have basically a gradient in magnetic field, okay. And if you talk about the field lines, they are not straight, they are like a curvature, okay, like here. So one can, with this kind of feature, we can observe three type of motion. One is gyration, that is around field line particles will gyrate. Another is the bounce motion, because at pole basically we have stronger magnetic field, so particles will go to the pole, then it will again bounce back, okay. And then we have curvature, okay. So with that one, the particle will even drift as well, okay. So we have gyration, then bounce motion, and third is drift motion. So if we have these two equations, and if you use fourth order Anke-Kuta method, okay, then one can solve this equation numerically, and we can see like how these particles, electrons or ions, how they perform motion in Earth's inner magnetosphere. So in this particular simulation, this particular animation, this particular code is developed by one of my student, okay, Dr. Bharti's student even, Pankaj Soni. And to initialize this simulation, we have used a proton, that is H plus, with 10 MeV energy, okay. And we have launched at, inside the space from surface in the equatorial plane, if you go, at 4 Earth radii, okay. So if I launch that particular particle there, then how it performs these three kind of motion in space, we can see here, okay. See, this particle is like gyrating and then going to the pole and getting bounced back, okay. Along with that, one can see is drifting around the earth, okay. So it's drifting around the earth. So with very simple Range-Kutta scheme, one can visualize the particle motions inside the Earth's inner magnetosphere. Okay, so this is a very simple simulation code, but one can introduce some sort of plasma waves or some sort of complexities to study different sort of phenomena in space. Okay, so let us move to another slide. So now, as I said, the plasma is electron and ions. Okay, so let me introduce that first. It is basically plasma is nothing but gas. Okay, or I can say mixture of quasi-neutral gas that shows a collective behavior. Means from outside, if you see, number of electrons and ions will be equal, so it is like a neutral. Okay, and this plasma supports basically a variety of electrostatic and electromagnetic waves. Okay, so this particular block diagram shows list of wave modes supported by ordinary plasma. Okay, and means I can say in laboratory one can see all these electrostatic and electromagnetic modes. Okay, I will not name each and every waves from this block diagram, but I will focus mostly on this particular one example I will present from electrostatic category, that is acoustic solitary waves, and another one that is from electromagnetic category, basically electromagnetic category, that is electromagnetic ion cyclotron waves. Okay, so most of the waves mentioned here, one can see or one can observe in Earth's magnetosphere, and how one can measure those kind of wave features. One has to go for a spacecraft mission. Okay, we have to send spacecraft to the space to measure the fields and particles, and if you analyze those data, one can obtain this kind of different wave features in Earth's magnetosphere. Okay, so the thing is, to have this kind of waves in the magnetosphere, one needs some sort of free energy sources to excite these waves in Earth's magnetosphere. Okay, so basically, if you talk about these waves, they are non-stationary, means always these different waves propagate from one region to the another, and though they are like separated, okay, as I said, like several waves here, sometimes you can see they are coupled with each other. Okay, and these wave processes, all plasma processes linked with these waves are highly nonlinear. Okay, very turbulent. So to handle them or to model their complex nature, it's very difficult to go with a single technique. Okay, that can go well with 100% modeling of these waves. Okay, and as I said, to excite these waves, one needs free energy sources. So when you talk about Earth's magnetosphere, we have, as I mentioned, the magnetic field. Okay, Earth's magnetic field lines, basically. So that has gradient. Okay, from equator to pole, when you go, we have a non-uniform magnetic field. Okay, and even non-uniform electric field. Okay, and the plasma densities, different regions support different plasma densities. Okay, and in charged particles, velocity also is different, and they have different pressure. Okay, so all these factors basically contribute for the excitation of different waves in Earth's magnetosphere. And along with this one, basically, the time varying non-uniform electric and magnetic field. Okay, because this electric field and magnetic field in space, it varies with time. Okay, so this kind of time varying feature of field can also generate waves in Earth magnetosphere. So if you say, like as all these conditions, what I have mentioned here, okay, that are present everywhere in Earth's magnetosphere, okay. So one can say that, or if we see the spacecraft data and analyze that data from different regions, different regions in Earth's magnetosphere support lot many plasma wave processes, okay. So that's the message from this slide. So as I said that these wave processes basically are very much complex. So with one technique, it is almost difficult to model them or study them. So here I have mentioned three methodologies, what generally or mainly we adopt. The first is a theoretical approach. It is, you just need a pen and paper, nothing more than that. With just that, you can use some sort of mathematical, mathematical, you can say like differential or ordinary or partial differential equations. You can solve by using some sort of, by assuming some assumptions, and then you can get the what you call analytical expression or analytical equation for one particular modes, okay. So that is first. And second is spacecraft observation. So one can plan a spacecraft mission, okay. And I think many of you may be aware, our ISRO, a space agency, Indian Space Agency, also planning many sort of spacecraft mission these days, okay. This spacecraft observation, basically, it's quite expensive. As you know, it takes a lot of time to build a payload on this spacecraft, and then, a planning as well. But it gives you in situ measurements of field and particles in space. So in that way, it's more realistic, okay. And third is computer simulations. Of course, if you have a big computer like computing clusters, then one can model, okay, the governing, if you have governing equations of this magnospheric plasma, by adopting some sort of numerical schemes, you can develop different simulation codes, and one can study these wave processes, okay. So in theory, basically, we have two main uh, theories. One is fluid theory. So in that, we consider like plasma is, sort of one fluid, okay. So the characteristic of individual particles get lost in this particular aspect. Another is kinetic theory, where we use basically individual particles, okay, and considered in terms of, plasma particle distributions, okay. So that helps you to model these waves in quite, a realistic way. But problem with this theoretical model is, they're quite complex to get analytical solutions of the waves. And in such a case, one has to consider lot many assumptions for the simplicity, okay. And in that case, you will lose some sort of even physics by assuming some assumptions. So you don't get really a complete picture of these wave processes, okay. So that's about the theoretical approach. Anyway, we are not going to talk much about that one. I have just introduced these two concepts. Now another, as I said, spacecraft observations, okay. So this is a picture which shows you different spacecraft missions, okay, starting from, we can say like the first artificial satellite, Sputnik 1, was launched in 1957, I think. And after that, we have many space missions, okay, many space missions by different agencies. So if you see now, so it's an evolving heliophysics system of observatories. Okay, so this picture shows some of the latest mission even. Okay, if you see the latest, if I talk, then solar orbital is the latest one, launched in 2020 by European Space Agency. And the solar probe before that, it was launched by NASA. So these two spacecraft are, the closest to this, like they are the object so far called like very close to the sun. Okay, so to study the coronal region of the sun. Okay, in this particular thing, I think Indian Space Agency ISRO has also planned to send one spacecraft. The name of that spacecraft is Aditya L1. Okay, and which will go into this line. Okay, at this place, this Soho, Ace, and Win. So this is basically they call L1 point. So at this place, our Indian Space Agency has planned the mission. So it will fly in year 2022, I think. Okay. So this was about the spacecraft observations. Okay. And now what these spacecraft basically do. Okay. These spacecrafts will have different payloads. So when you talk in terms of plasma, okay, so we focus on like plasma measurements, like charge particle measurements and the field measurements. Okay, these two measurements are very important to model or to investigate these plasma wave processes in Earth's magnetosphere or any plasma environment. Okay, so whatever measurements after this slide I will show, either they will be in terms of plasma density or electric or magnetic field measurements in space. Okay, so let me start with some of the observations of the wave. Okay, yeah, and in next slides I will be mainly focus some of the measurements from cluster spacecraft, which was launched by European Space Agency in 1996, and some of the observations from RBSP. The name of this spacecraft is changed now, they called Van Allen. Okay, this particular spacecraft was sent to explore the Earth's radiation belt region in year 2012. Okay, so I will only show two or three examples from these space missions. Okay, so here is the one. Uh, Observations of solitary waves in Earth's magnetosheath region. Magnetosheath region means, as I said, like when the solar flow of charge particle, that is solar wind, uh, firstly meet at the Earth's magnetic field, we have bow shock, and just after bow shock, okay, behind that we have a region called magnetosheath. Okay, very turbulent region, one can say. So in this region, the cluster spacecraft has observed a series of coherent electric field pulses. Okay, coherent electric field pulses. They are shown in this particular panel. Okay, so if you see, they are very nicely aligned. Okay, larger amplitude, then smaller, and smaller. Here one, here one. So they are either coming or like they are observed in a single pulse or like series of wave pulses. Okay. So if you take a spectra, okay, yeah, before that let me tell you, this electric field measurements or magnetic field measurements I'm talking about, they are high resolution. Okay, high resolution means you have a data of like less than millisecond time. Okay, each point. So one can, if you have this kind of uh, high resolution electric field data or magnetic field data, then we can see this kind of features. Okay, so these are nothing but solitary waves. Okay, and if you take a spectra, okay, if you apply Fourier transform and obtain the dynamic spectra, then you can see, okay, the frequencies. Okay, it's up to few kilohertz. Okay, up to nearly 50-60 kilohertz. Okay, here, even here also. So this cluster spacecraft basically consists of 4 spacecraft. It's a cluster, basically cluster of 4 spacecraft, and they sometimes keep they are always moving in a space in tetrahedral shape, keeping distance between them like sometimes very close to like 20 kilometer or up to 100 kilometer and all. So with this kind of geometry in a space, when they are propagating, it's very useful to see the activity, wave activity, which appear on one spacecraft, how it appears on another. Okay. So in that way, this data, this spacecraft mission was like, very useful. This was first multi-spacecraft mission. Okay. So if you see these 2 panels, the broadband wave spectra, okay, here and here, this is observed by spacecraft number 3, and this is by spacecraft number 4. The spectra is nearly same. Okay. That means these waves, basically, these electric field pulses, are propagating from one spacecraft to another spacecraft without losing their shape. Okay. So they are like waves that you can see in water. Okay, solitary waves, or you can term them like soliton one. So it propagates in a medium without changing their shape or size. Okay. So what is shown by many studies is that this particular wave modes, basically, they trap the energetic particles inside them. Okay, these electric field pulses. Yeah. And speed of these wave pulses are like sometimes 1,000 kilometer per second. So just imagine they are capturing charged particles and taking this particle along with them from one region to another region with so fast. So one way they are responsible for a plasma transport. Okay, as I said, the solar wind particles, how they are entering into Earth's magnetosphere. Okay, in different regions we have different plasma characteristics. Okay, so these are the waves, basically. This is one among all the waves responsible for plasma transport. Okay, so this was the first observation about the solitary waves in Earth's magnetospheric region. Let us move to the modeling part. I'm coming, I'm showing some sort of observations and then coming to, link some sort of computational modeling aspect, because I I think there are some people who might be interested in this simulation. So in this talk, I am mainly focusing on fluid simulation. So plasma is considered as a fluid. Okay. So in this technique, basically, the governing equations are the continuity equation, this one, then equation of motion, okay, and then this is energy equation, and all these equations are, linked with the Poisson equation, okay, and once you have this kind of equations, you can adopt some sort of numerical schemes, okay, to solve these equations. So in this one, we have basically a time derivatives and we have spatial derivatives, okay, in all those equations. To solve them, okay, for spatial derivatives, we have used fourth order finite difference scheme, okay, which is given by this equation. In this equation, FH represents like a physical quantity, maybe a field or maybe density or temperature at one particular grid H, and this delta X is nothing but a grid spacing. Okay, so what I have done is, like, this is 1D fluid code. So what I have done is I have system and then I have divided that, okay, uniformly by considering a delta X. Okay, and on that particular grid point, I have solved these governing equations of plasma. Okay, and for time derivatives, I have used leapfrog method, which is second order accurate. Okay, and if you talk about this kind of simulation, then it always excites a numerical noise, and once you have noise, then your simulation will have some problems or errors may occur. So in that case, you have to use some sort of filtering, okay, numerical filtering. Okay, so I have not included that particular aspect in this slide. And then one has to go for boundary conditions. They are very important in the simulation. So just for a simplicity in this simulation, we have adopted periodic boundary conditions. Okay, so yeah, so this particular simulation basically this particular simulation we have used a density perturbation as a to initialize. Okay, so why we have used a density perturbation, let me tell you. When I'm talking like flow of charged particles coming from the sun to the Earth's magnetosphere, okay, so there is always a situation that like some extra charged particles are getting added into background plasma. So it's like some sort of localized density enhancement you can see in different regions of Earth's magnetosphere. So that's why we have used uh, density perturbation. And in all this, in this particular simulation, we have used Gaussian type. Okay, so Gaussian means a very localized, you can say, a perturbation you can introduce in your simulation system. Okay, so with that one, if I initiate, okay, I'm not showing all the parameters or variables that we have obtained in the through this simulation, but I will mostly focus on electric field and electrostatic potential associated with that structure, so that we can see this kind of electric field pulses, okay, in simulation. That is our motive here. So let me run, okay, this simulation. Yeah, initially at 0, okay, at position 0 we have introduced the perturbation, and then we have see like the pulses are formed, one propagating in negative direction of this axis and one positive direction. Okay, and you see with time, okay, earlier it was like just a single pulse. Okay, now it is split into 3. Okay, and if you go beyond, then you will see, okay, a series of wave pulses have occurred. Okay, so if you see, it's like initially one pulse is appearing and then it's breaking into 3. So this particular phenomena, of generation of solitary wave pulses or series of solitary wave pulses through wave breaking, basically, so far it was not reported in space, or you can say uh, Earth's magnetosphere. Okay, this was first time we have model, and this is published in this particular journal. Okay, so if you talk about this particular wave pulse, they are very much coherent and stable. Stable means they propagate from for a very long distance with a speed of like 1,000 km per second without losing its shape and size. That is what like we have proved through this simulation. Okay, so this was one example. Now I will move to another example. Okay, earlier we have seen like bipolar electric field structure or bipolar electric field pulses. Now this is example of monopolar electric field structures. Okay, they are electrostatic, and mostly they propagate along background magnetic field lines, okay, in Earth's magnetosphere. So this particular observation comes from Van Allen probe, name of the spacecraft. And when I'm talking about this monopolar electric field pulses, basically they are also known as double layer. And these structures, these double layers, basically it is believed that they are formed due to parallel layers of opposite electric charges. Okay, so there are some regions in Earth magnetosphere where you can see this kind of picture. It's this particular waves you cannot see everywhere in Earth's magnetosphere, but very specific region. So one is Earth's radiation belt region, where you can see series of a monopolar electric field structure. You can see here, okay, or here. So here, like their amplitude is positive. Here their amplitude is negative. Okay, and if you see the spectra, okay, wave spectra, dynamical wave spectra, then you can see their frequency is like almost like 10 to more than 1000 kilohertz, okay, 1000 hertz, okay. So associated with this, you can see a density variation, okay, and from this wave spectrum, okay, if you take a waveform data of hardly 4 or 5 milliseconds, then you can see this series of wave pulses or electric field pulses in high resolution electric field data. Again, from this, if you take less than few millisecond, okay, less than 1 millisecond data, then you can see this kind of monopolar electric field pulses in the data, and they are called double layers. Okay, so we have tried to model this particular formation of double layers through fluid simulation. This particular simulation code was developed by Dr. Ajay Lotekar, who was my student. So in this one, what we have done again, we have used localized density, okay, localized plasma density perturbation in the system, okay, and then once we introduce that, you can see, yeah, this is very fast, but if you see this structure, how it's sustained, okay, very nicely propagating to one particular direction with constant speed, okay, and after, but here something is happening now, and you can see earlier it was bipolar feature, but with time it has reduced, okay, to a monopolar along with some sort of shocklets, okay. This particular form of electric field pulses behind this one are called shocklets, okay. So this is a monopolar electric field associated with the double layer, okay. So this is perfectly, you know, that particular simulation perfectly explain the generation of this kind of this kind of solitary waves or double layers in Earth's radiation belt region, okay. So this was a simulation for double layers, okay. So let me go to another example. So far we have studied only the electrostatic waves, okay. These two examples, bipolar and monopolar electric field structure associated with solitary wave and double layers, they were like, you know, propagating along magnetic field line, and they were electrostatic. So there is no field perturbation associated with that. Now we will move to another example we call electromagnetic ion cyclotron waves, which are observed in different regions of Earth's magnetosphere, but we will focus mainly their observations in the radiation belt region, okay, because I have linked some of the slides to one particular phenomenon, so that's why I have chosen that particular example, okay. So here is an example from Ares satellite, which was launched very recently by Japanese space agency, just I think 3 years back, okay. So this is one of the magnetic field component, okay, observed by a spacecraft, okay. So BX, and if you take a spectra, okay, dynamic spectra means applying Fourier transform, then you can see this kind of spectrogram, okay. So this red emission sort of features, okay, they are rising tone emissions, okay, frequency emissions in this frequency range, okay, of few around, you know, less than 2 hertz. And if you analyze this structure, this particular waves, then you will see that they are associated with hydrogen or helium ions, okay. So this particular waves are called electromagnetic ion cyclotron waves, okay. And this was from space, of course. Now, whether this wave activity or wave sort of processes happening in Earth's magnetosphere, whether you can see it on ground, okay. So in that case, I am showing you one example. So this electromagnetic ion cyclotron waves observed in inner magnetosphere, sometimes, they propagate to the high latitude region and where they get leaked, and you can observe them on Earth's surface, okay, especially high latitude region or polar region. So here is an example of observation of electromagnetic ion cyclotron waves. Again, here this is these are the fluctuations in magnetic field data that is captured by induction coil magnetometer, which is installed again at our Indian Antarctic station Maitri. Okay, Maitri lies here at this red point. Okay, so this particular experiment is run by Indian Institute of Geomagnetism from year 2011. So we have like around 10 years data, and we are utilizing it to probe the inner magnetospheric processes. Okay, so you can see very similar features of these waves, okay, in space and then ground. Okay, so are these waves basically playing any sort of role? That is question. So yes, these waves play a very important role in precipitation of MEV range electrons. MEV range electrons. Details of that I will give it in my next slides. Okay. So I was talking about electromagnetic ion cyclotron waves. Okay. So when I talk about its generation mechanism, basically, you just imagine the Earth's magnetosphere. Okay. And I was telling you equatorial plane. Okay, so in equatorial plane, I was telling you the magnetic field will be lesser compared to the polar region, right? So in that particular plane, sometime if there is a push, okay, push of solar wind, it will compress the Earth's magnetosphere on day side. Okay, and that particular phenomena creates pressure anisotropy in that equatorial region. Okay, and it will excite some sort of instability, ion cyclotron instability we call. This instability occurs because of the pressure anisotropy with the ions. Okay, so once these EMIC waves, electromagnetic ion cyclotron waves, excite in this region, okay, which is shown here. Yeah, you can see here. Okay, this is Earth, and we have this magnetic field line. So this is equatorial region where I have shown some sort of feature, which is again close view of this is represented here. You can see some sort of EMIC instability is occurring, and then waves are excited. Okay, so basically this equatorial region is the source of these EMIC waves in inner magnetosphere. Once these waves are excited, then what they will do, they will propagate. Okay, they will propagate along this magnetic field lines towards the high latitude region. Okay, now this high latitude region is again expanded here. You can see we have ionosphere. Okay, high latitude ionosphere. So high latitude ionosphere basically it acts like a duct for these waves. Okay, these waves entered into ionosphere and then they propagate in this duct. Okay, ionospheric duct. And while propagating, basically, while propagating, they scatter, they interact with the charged particles. Okay, so wave particle interaction happens, and sometimes the particles get scattered, and then they will precipitate into the Earth's upper atmosphere. Okay, and as I said, once they precipitate, then they interact with the atmospheric gas molecules. Okay, they excite them, and then they emit colors in the form of aurora. That's what exactly is shown here. Okay, so you can see around 300-kilometer region, this altitude, we have this sort of aurora. Okay, and sometimes while propagating this inside this ionospheric duct, okay, if the ionosphere permits, means there are certain conditions. Okay, if that conditions happen in this ionospheric duct, then this these waves basically get leaked through that duct, and you can observe them on ground. Okay, so as I said, India has two observatories or station in Antarctic region. One is Maitri, and another is Bharati. Okay, so we have this induction coil magnetometer experiment installed on both stations. Okay, so this was one particular aspect of EMIC waves in uh, high latitude region. Okay, so I was talking about particle precipitation. Okay, so as I said, particles will have different energy levels, right? So different energy levels, different energies. Okay, particles with different energies, they will penetrate at different altitude. Okay, so to show this particular process, basically it is very difficult to do investigate this particular process through observation. So in this kind of scenario, you have to go for computer simulation. Okay, so this particular figure is obtained from GN4 simulation code. On y-axis we have altitude, and on x-axis we have energy. Okay, so the thing is that what this figure tells you is that particles with higher energies, okay, they comes deeper to Earth's upper atmosphere. Okay, so problem is that you just imagine like particles with MeV energies, when they come to upper atmosphere, where you have some sort of neutral atmosphere as well. Okay, so they are depositing their energy. Okay, so they are depositing their energy means they affects basically the global ionosphere and atmosphere dynamics. Okay, so though this particular particle precipitation phenomena is happening in high latitude or polar region, around polar region on both poles, okay, but it affects global atmosphere ionosphere dynamics. Okay, and that's why it is very important, okay, to study this particular aspect. And what is responsible for this precipitation? I have already mentioned. These waves, actually different waves, interact with the charged particle. So because of wave particle interaction, the trajectory of particles, basically, as I said, they were propagating along magnetic field lines, right? So once they interact with some sort of waves, for example, EMIC waves, electromagnetic ion cyclotron waves, then their trajectory gets changed, and rather than following that particular field line, they will enter into Earth's atmosphere, and they change the global atmosphere ionosphere dynamics. So that was one aspect. Now that was about particle precipitation. What about particle acceleration? I was telling you that the Earth's radiation belt has particles with MEV energies. Okay, like outer radiation belt has electrons, MEV electrons, and the inner belt has MEV ions. Okay. So what is responsible for that kind of energization? Here, the schematic explain that particular phenomena, which is very recently proposed by Moser, okay, in year 2030. So here, the schematic shows this is Earth, and as I was telling, the dipolar magnetic field configuration of Earth's magnetic field. Okay, so inner magnetosphere. Here we have outer magnetosphere, this one. Then this is inner magnetosphere, inner radiation belt. Okay, so here I have shown series of double layers. Okay, and then they are coherent, as I mentioned. Okay, in simulation also we have seen that these are very coherent electric field pulses. Okay, so what happens first, the particles coming from, the solar wind particles, whose energies are like, EVs, EV, electron volt basically. So they interact with these coherent wave pulses, okay, double layer pulses, and they gain energies up to some keVs, means kilo electron volt, and later they interact with another wave, okay, in different in other frequency range, that is ultra low frequency or very low frequency waves, okay, and they gain energy in MEVs, okay. So this particular process was known earlier in Earth's radiation belt, but this realistic picture basically was confirmed by Van Allen spacecraft, which was launched by NASA in year 2012. Okay, yeah, this spacecraft Van Allen. It consists of two spacecraft basically. Okay, so this is the feature, of one feature we can say of the plasma waves. uh, so it's not one wave, like couple of waves. Okay, they interact with the particles and sometimes they gain the energies in MEV. Okay, so this particular aspect is very similar to the particle accelerator, what we know, the people in nuclear physics especially, they or particle physics they used. Okay, so this was one. So whatever slides I have shown basically, I would like to conclude with this slide. So plasma waves in Earth's magnetosphere, I have shown you that like how they plays a role in plasma transportation from one region to another. As I mentioned, like from solar wind, how they travel to the inner magnetosphere, okay, and then they precipitate even Earth's upper atmosphere, and then they change the global, dynamics of upper atmosphere. Then second is particle acceleration. So solar wind particles with EV energies, how they gets accelerated or energized, that I have shown. And we have shown that like in this process, the waves, basically wave processes, they play a very important role. And third is particle scattering. So like particle scattering means because of particle scattering, I have shown you that like how these particles are precipitating in the Earth's upper atmosphere. Okay, so basically, what is like different techniques I have shown you people, like theory, then spacecraft observations and simulations. As I mentioned, the spacecraft observation basically gives you in situ measurements of fields and particle, and with that kind of measurements, you can extract the information on waves. Okay, however, it's very difficult to, because when you talk about the spacecraft, it is moving from one region to another with some speed, right? So whatever comes into its way, it's capturing that information. So it's basically a snapshots, right? Snapshots of particles or field. Huh? So it is very difficult to, or you can say incapable to provide the evolutionary information of any plasma wave processes happening in Earth's magnetosphere or any plasma environment. Okay, so to investigate this evolutionary characteristics of any plasma wave processes or any processes happening in Earth's magnetosphere, you need to have computer simulation techniques. Yeah, that is very much necessary, because once you have this information, okay, snapshots taken from spacecraft. I mean, snapshot means the field measurements or particle measurements from spacecraft. Once you have that information, means you have initial conditions that you can set up. With that one, you can set up your computer experiment. Okay, and then with that initial conditions, if you run your codes. Okay, I have shown you only one or two, two codes: test particle simulation and another fluid. But there are variety of simulation techniques with which you can extract micro level information which you don't get from spacecraft missions. Okay, so just to conclude, as I said, Earth's magnetosphere basically provides you a natural lab. Okay, we don't have any restrictions on the boundaries, right? So to study any particular or any kind of plasma wave process, uh, you can tackle very nicely. Okay, and with those investigations, it will be very useful to use that kind of the physics extracted from that particular simulation. Okay, can be used in laboratory, and of course that can be useful for certain experiment which will be useful for mankind. Okay, so as I said, like particle accelerator and all, so this kind of things, or even when I'm talking about the inner radiation belt. Okay, so that is a region where our most of the satellites lies. So International Space Station. Okay, International Space Station also, dose of radiation is very important for us, like importance to study, because it is very harmful for astronauts. Even sometime, as I showed you, coronal mass ejection coming towards the Earth. Okay, so sometime that kind of process triggered a storm called, we call actually a magnetic storm. Okay, because you will see a lot of disturbances in the geomagnetic field recording on ground or in space also. Okay, so those kind of phenomena are very very dangerous for uh, especially the countries which are in high latitude. Okay, so to conclude, basically all this information is very much useful for mankind. Okay, so with this I will end my talk. Thank you very much for your attention. I hope I have finished. Oh, I have taken, I think, 20 minutes.
Yeah, it is fine. It was. Thank you very much for a very interesting talk. It was really a lucid talk, and you are really made it look simple. Though I know that
This
computer simulations can really become very difficult.
very difficult.
But it was a good. Yeah, it was good for the students to understand the importance of computer simulations.
Yeah.
Right, because there is a confusion. Sometimes people think computer simulation is same as animation, but I think you
Yeah,
have
yeah.
clearly brought it out that it is the reproduction of the phenomena or prediction of the phenomena from the governing equations. That is more
Yes.
important.
Yeah.
And the equations involved here are partial differential equations, which are very difficult to solve.
Yeah.
So actually, it was really difficult work. Dr. Kakad has really simplified and presented it to you. I hope you will make use of this knowledge. There are some questions. We will
Yeah, sure.
question from Rahul Yadav. He is asking, does the CME effect or affect the Earth's magnetosphere or atmosphere equally throughout the revolution period?
Equally throughout the.
The revolution, perhaps Earth's revolution period.
Oh, yes, yes. It's basically when you talk this CME, that means related to, as I said, like global this geomagnetic storm. It's a global phenomena. Yes, of course. Like day side and night side, it acts differently. Yeah, and it all depends again on the strength of CME as well. Okay, so depends on day and night, like where our location falls, we will have different effects.
And different months.
No, no, like not much. Yeah,
Okay.
not much means it will not affect on like any month. It will be same. Yeah.
Okay. So students can ask questions in the chat box. There's a next question by Zumana. She's asking what is grid. I don't know which part she has asked it at 3:50.
Sir, actually,
Yeah. Go
so
ahead.
can I say that was something
Yeah,
like
Clark.
once the equation slide was shown, after that there was a slide where it was written grid H. So I
Oh
didn't
yes.
understand.
Yeah. As I said, that was a term used in simulation. Okay, so just consider one system. Okay, or maybe you can say your mobile phone if you take. Okay, so if I divide that area on the screen with uniform distance, okay, one line, okay, one like that. So this particular system, a complete system, I am dividing into a small cells, okay, and that border of that cell is nothing but the grid point, I can say, because to solve these differential equations you need grid points. You cannot solve like continuous, right? So that terminology we call a grid. Whether you
Yes,
got
sir.
what I
Yes,
said?
sir, I got it. So there was one more question. When it comes to plasma, I had seen this experiment on YouTube with grapes. So I read up a whole paper on it. Needless to say, I didn't understand a thing.
Mhm.
So would you explain something on it if you know?
Can you repeat your question
Yeah.
once?
There was this experiment on grapes. Like you cut the grapes and you put it in a microwave, and
Grape.
there is yes grape,
Yeah, grape,
and there
grape,
is plasma
Draksha.
developed.
Okay.
And there was a whole experiment done on it, research paper done on it.
Okay.
Over there, they had kept two grapes in contact, and there was a something called hotspot in the grapes, which was the center region of the grape. And if you keep the grapes apart, then there is, I think, there was no plasma. And if you keep it in touch with each other, then there is plasma sparks generated where the grapes touch. So I didn't understand that you can say
Uh,
mathematical and theoretical part of it. I just understood the concept.
okay. I'm sorry, but I'm not aware with that kind of experiment so far. Is it published paper?
Yes, it is a published paper. I think I have it. I don't have to see. It was
Any,
posted on YouTube by Veritas CM. There
Okay.
is this YouTube
anyway,
channel.
this is Jumana. This is going little away from the topic.
Yeah.
We
No,
can discuss
let
it
me go
later.
through.
Yeah,
Yeah. Okay.
yeah. You can send him the paper and then we can discuss it.
Yeah, you can share
Okay.
that paper with me. Yeah.
Okay. Thank you, sir. I'm sorry.
Thank you. Thank
Yeah, it's fine. No, it is good. So there another question by Aniruddha Shinde. So why there has been no equilibrium on the surface of the sun for the sunspots?
you. Equilibrium.
On the surface of the sun for the sunspots.
Okay. Basically, these black spot we call sunspot. They constantly, of course, they are not uniform. First of all, they are not fixed at one position. Okay, they are going, coming towards the equator, and then with time they move towards, pole. Okay, so what is responsible for that? I am also not that aware because that's again a solar physics related question.
Yeah, it's a very highly known. Yeah, there's another question by Anjali Prajapati. So can we collect plasma coming from the sun for research purpose on the Earth?
Oh yes, yeah. Like with the help of spacecraft, we are gaining lot much knowledge in this natural plasma laboratory. Okay, and with that understanding, we are creating that sort of plasma in the laboratory. If you see a recent news about, I think, China and one about Korea also, they are talking about making artificial sun in laboratory. Okay, So with which they are planning to generate energy. Okay, how much success they got it, I'm not aware, but this news was very much, highlighting in last 4 or 5 months back.
Yes. Yeah. I have one question. In your first simulation of the particle gyrating in the Earth's magnetic field, you have taken the inner magnetosphere,
Yes.
and I mean, what does one observe similar thing if one does it in the outer magnetosphere? What happens?
Oh yes, we can consider. Actually, this particular code will work only for a close magnetic field lines. Means the field lines which is pole to pole is getting connected. So once you go outer and outer side, then field lines in this polar region basically they gets open. Okay, so what will happen? This particle while performing bounce motion, it will precipitate there itself because the field line is open.
Okay.
Yeah, so this is basically only for inner magnetosphere where field lines are dipolar and closed.
Okay. But then, if there is a component, a radial component to the initial velocity, uh,
Hmm.
then will it go towards Earth?
Oh yes, yes, that will change the trajectory. We don't know where it will go, but that will certainly change trajectory. This was very simple simulation because we have just a dipolar Earth's magnetic field configuration and then injected one particle at one magnetic field line. That's it. So the complex things really, that is like we have already planned, like putting waves and then giving initial push to the particles, like how the motions will affect. That we are going to study.
Okay. So, because your initial simulation where the solar wind coming from the sun, it
Yes.
bypasses Earth and goes to the darker side.
Yes.
It is
Yes.
perhaps that is difficult to understand. Why doesn't it hit
Yes.
the sun and
Yeah.
Earth from the day side? Yeah.
Yeah. Like on this slide, this B basically,
Yeah.
this form is very much systematic to solve. Okay. But if we want to consider whole uh, Earth's magnetosphere, basically, it will be possible, but it will be somewhat complex to study, particles behavior in that kind of magnetic field configuration. But again, there are models like
Okay.
yeah, this B, how it represents the configuration what you have said. For that also we have models, so one can adopt those models in this simulation codes and one can investigate the motion of particles.
Okay. Yeah. There's one more question from Sachit Upadhyay. Is it true that the more the number of sunspots on the sun, the more vulnerable the sun becomes?
Yes, yes, and that will have effect on even Earth's magnetic field environment. So that's why when there is a peak in Earth's this solar cycle, so we call that is the active period of sun. So most of the magnetic storms or solar events happens in that particular time. So
Okay.
basically knowing or prediction of the solar cycle again it's very much required because to plan this spacecraft mission. Just a minute, I have phone call, I will. So any planning any spacecraft mission, okay, because we will have certain goals. Whether I want to send a spacecraft mission to space when sun is white, okay. So I have to choose that particular. Okay, I have predictions of solar cycle. So I will choose a duration, okay, or years where sun is white, okay. Then if my motive is to study the Earth's magnetic environment when we have sun in active phase, then one has to choose that particular duration.
Okay, I think there are no more questions, so we will stop here. And again, thank you very much for the talk. And my colleague, Dr. Vaishali Raikwar, will propose formal vote of thanks, and then we will end the session. Vaishali, madam, please.
Thank you, sir. Honorable Principal, Dr. Himanshu Dauda, Director, Dr. Usha Mukundan, Head, Department of Physics, Mrs. Ratna Jadhav, today's invited speaker, Dr. Amar Kakad, and all my colleagues and dear students. On behalf of Physics Department, I express my deepest gratitude to our today's speaker, Dr. Amar Kakad, for accepting the invitation and delivering this lecture on various plasma wave processes in the Earth's magnetosphere. Sir, you explained all the terminologies, complex terminologies in a very simple manner, because some FY students, FIBSc students also attended and they asked the questions also. They got interested in it, and there's various simulation processes using like various schemes, Rangakutta schemes and all. You explain it very well. The role of EMIC waves in space in explaining the aurora, various solar spots, Earth's magnetic field, coronal mass ejection, and how the magnetic cavity protects the Earth from these solar winds. All the information was delivered in very lucid manner to the students. Thank you, sir, for delivering this talk. Thank you all for attending this talk. All the dear students, I think they are they come to know that there is very much there is many opportunities in the research field of Earth's magnetosphere. Thank you.
Yeah, thank you very much.
Okay.
Ratna madam.
Thank you.
Thank you, Dr. Kakad, for such a wonderful and insightful lecture.
Thank you, ma'am.
You have really explained plasma waves processing and Earth's magnetosphere in a very lucid manner. Thanks once again. And thank you, everyone.
Thank you.
Okay.
In the
Yeah,
session.
I will end the meeting.
Yes, we will end the session. Thank you, sir.
Thank you. Thank you. Thank you very much.